Great, thanks very much. So my name is Matt. I'm a postdoc at the University of Cambridge. I'm going to be talking about the environmental dependence of the I-band secondary maximum. So this work has really been significantly motivated by the mass step. So this is a pretty well-established phenomenon at this point. We find after we apply our standard stretch and color corrections for Type Ia supernovae, we find that their standardized peak at absolute magnitudes show an environmental dependence. Specifically, those in high mass galaxies are slightly brighter than those in low mass galaxies. And there's been kind of a lot of ongoing discussion in the field about what's the root cause of this. Is there some kind of interesting intrinsic difference between these two? Maybe there's something different in their progenitors, maybe different progenitor channels, different populations of objects, and so on. Or maybe there is actually just one overall population, and they just happen to look different because of the effect of dust reddening from dust in those galaxies. Maybe those dust properties are different. So it's kind of really important trying to understand this both from an astrophysical perspective and from a cosmological perspective. And we're going to be thinking about that today using this model called Bayesian. And for those who aren't familiar with it, Bayesian is a probabilistic SED model for Type Ia supernovae. So the goal here, this is an empirical model. What we're trying to do is put together some model for the time and wavelength dependent SEDs of Type Ia supernovae with a bunch of different components going into it. So I'm just going to kind of quickly go over what's going in here. So we're assuming that there is some mean intrinsic SED of Type Ia supernovae across the population, just overall population mean. We have the first component is basically kind of a stretch-like variation, so analogous to kind of X1, so some kind of stretch variation on the SED. On top of that, we have an explicit dust extinction law. So we have some parameter RV that describes the slope of that dust extinction law, and then AV, which represents the amount of reddening, basically, or the total amount of extinction just corresponds to the amount of the dust. And we also have some distribution of kind of stretch independent intrinsic colors of Type Ia supernovae. So if you stick together mean SED, some kind of stretch-like variation across the population, dust extinction, and the intrinsic color, stick them all together, you get a model SED. And you can take that, integrate it through different photometric filters, to get different redshifts, phases, and so on. And that will give you model photometry. And you can compare that to your observed data, and then you can just take this model and throw a whole bunch of supernovae at it. This is a hierarchical Bayesian model. What that means is we're trying to infer the properties of the overall population. So chuck a bunch of objects at it, you can infer, for example, okay, what is the stretch-like variation? How does stretch affect the SED across the population? What is the overall population distribution of RV and AV, for example? So that's the basis of what we're trying to do here. Now, how can we apply this within the context of the mass step? So, like I mentioned, we have this ongoing debate about is it an intrinsic difference, some difference in the mean intrinsic SED, or is it just the result of dust? Maybe it's just some difference in dust extinction term. How can we tell those two things apart? Well, what the advantage of what we can do when we're doing this kind of population inference is we can allow for separate populations or separate population distributions for or on either side of the mass step. So separate dust distributions and also differences in the mean intrinsic SED. The reason we can disentangle these two things is because dust, there's only so much you can do with dust. You can change the slope of the dust law and you can shift it up and down, but you don't have that much flexibility to affect the underlying SED. So if the differences in your data aren't consistent with dust, they'll be captured by the mean intrinsic SED component instead. So that's the principle of what we're trying to do here, to disentangle them. So again, throw a bunch of data at it, see whether the data tells us the mass step seems to be intrinsic or dust or some combination of the two. That's what we did. Okay, kind of skim over this, but the question of is it dust or is it intrinsic? We put out a couple of analyses on this year. So we did a combined analysis of DES 3-year foundation and pan stars, more recently an analysis of DES 5-year. In both cases, we found evidence supporting the idea that the mass step is at least partially driven by some intrinsic difference. Dust may play a role, but there does seem to be something intrinsic going on. But that is just thinking about the mass step as people have typically done it in the field, of thinking of it as some kind of overall magnitude offset between your two populations. But there's no reason why that necessarily needs to be the case. The advantage of working in this Bayes-N framework is that we can extend this to consider time and wavelength dependent intrinsic differences between Type Ia supernovae on either side of the mass step. And that is what you can see here. So think about that mean intrinsic SED on the previous plot. All I've done is once we infer that, we can just integrate through filters and work out, okay, look at it in the space of light curves. What does that mean intrinsic SED look like? So what this plot shows is so this is without any dust. So AV set to 0, just taking the intrinsic part and comparing Type Ia supernovae of the same stretch. So the only thing that is different between these two is that they're on either side of the mass step, the kind of overall population mean. And the most notable thing you can see looking at that is we see this very significant difference around the secondary maximum in I band. So compared to what's going on at other times, this is much, much more prominent. This is about, on this data set, this was, again, that kind of combined sample analysis. This is about 4.5 sigma significance. It seems like generally in the high mass galaxies, or supernovae high mass galaxies, are both brighter and seemingly peaking a little bit earlier based on this data set. I did the same thing on the DES 5-year data, and we found the same thing. So we're seeing this kind of brighter and earlier peak. Something is causing, some effect is causing this intrinsic difference, and specifically it's materializing around the I band, at least as you go into the infrared at around these phases. So this is a further piece of evidence to support that there is some kind of intrinsic difference between Type Ia supernovae in different environments. So what's causing that? Part of the reason I wanted to give a talk here today was because there's a lot of people in this room who know a lot about Type Ia astrophysics who may have some ideas on this, and I would absolutely love to discuss with you. So Case in 2006 made some predictions about how metallicity would impact light curves. Specifically, they predicted that metallicity should have a stronger impact on the secondary maximum than it would around peak. Maybe this would be some kind of metallicity effect. And we'll also see this is specifically in the I band, not in the R band. So Maxine Deck has recently put out a paper looking at the secondary maximum in ZTF, also found some differences between the behavior in R and I band of the secondary maximum. They're not looking at environment, but seems to kind of, maybe there is something there. And I'll say we can't currently link this to a specific spectral feature. Bayes-N is currently only applied at the level of photometry. We do plan to apply it to spectroscopy in future. So hopefully going forward, we'll be able to make some more definitive statement about that. So just to finish up, so yeah, Bayes-N is out. It's all public code. We have a new GPU accelerated Python implementation that anyone can use, both to do this kind of overall population inference, and you can also use it for just single object light curve fitting as an alternative to SALT or Snoopy or something like that. We're also integrating into SNANA. It's now possible to do BBC fit using Bayes-N, although this is still kind of early work in progress stuff, but it is now possible. We also just put a new paper on the archive where we took Bayes-N and applied it to SALT-based simulations which had dust in to validate that even when we take it and apply it to a different model, we can still infer the correct dust properties, which is kind of a nice validation to see. That's why we also did this DES 5-year analysis. And yeah, so that's it really. So I'll leave you with my summary. Happy to take any questions.